Hello, welcome back to the class. And today we'd like to start our local strengths. We call the part 2. And this is the first session, so that I'd like to briefly introduce about what is the local strengths and how we're gonna connect the obtained outcome from the global strengths analysis and how that will be used for our local analysis. So I just put it like topic 9.5, but I will try my best to introduce the topic 10 to 12 that is related to the column buckling strengths and column collapse, and topic 13 to 15 we will discuss about the truss methods, and general truss will be introduced in topic 13, and how we're gonna handle these truss method by using joint as well as section method will be covered in topic 14 and 15, and lastly we will introduce the statistical analysis. So, and actually part 1 and part 2, those two are one set, so please remind all those things by studying the part 1 before we start part 2. So we are here. The aim of this lecture is we will discuss about basic concept for global as well as local analysis by introducing one-dimensional element, and the outcome might be we could be aware of the ship structural analysis, the whole procedure, and for the column as well as offshore structural analysis, truss, and we could be able to describe the basic structural failure of the structure. At the same time, we could remind about the boundary condition, that concept. So as you could see here, I just brought some local structural element. You might not be familiar with this, but this is come from the deck or the side shell or the inner bottom, outer bottom, doesn't matter. This is come from our ship structures, and you can see deck, side, bottom. So this is the combination of basically the plate, and this is the stiffener, and this is plate again, this is stiffener again. So if we combine all those things, it will be shaped like that. You can see here plate, stiffener, plate, stiffener. This is combination model. So basically in general we call the plate stiffener combination model. So as you could see here, this is stiffener, 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 the whole plate. So it's up to us. We can split here, then we can bring it here. The shape of this plate stiffener combination model is, this looks like simple beam, like I or H beam. You know what I'm saying? That was the reason why we have learned about the beam first. And at the same time, we can split differently, like plate and stiffener. Plate, stiffener, separation model. So basically, we can split into two. Categorize plate stiffener combination model number 1, and this is plate stiffener separation model number 2. But most of the time, we will focus on this one in this module. So you should be aware of, this is plate, this is stiffener, this is longitudinal direction. That's why we call the longitudinal girders. And here, this is transverse frames. So if those two, plate and stiffeners, are combined, we call stiffened panels. So that's all. So one of the example, this is the midship section for the oil tanker. Looks like Suezmax class. The length is 233. You could see here. So the length is 233, the B and depth. And this one, you might not be familiar with this. FS is frame spacing. This is common sense. Please have a look. Frame spacing in general, I will show you the details, but this is one frame spacing. This is generally like 5 meter for oil tanker, sometimes 4, sometimes 6, sometimes 4.5, 4.8, something like that. So nearly 5 meter. And In one hold, we have like 5 to 7 frames, right? So at the same time, this is midship section information. So you can see the geometrical information as well as the material properties here. AH, this means AH was 32. What was that? AH 32 means yield stress is 315 megapascal, right? Like here. This is mild steel, this is high tensile, and you can see all the details. This is the plate thickness and stiffness informations are given here. At least you should know how to read the design. So here, this is sectional view, and this is the one whole structures. So as I explained earlier, this is the overall, the whole shapes, and basically, for example, this is 1, 2, 3, 4, 5, 5-hold system, or a 7-hold, or 9-hold is up to the requirement. But basically, we can bring this one from the midship. So how many frames we have? 1, 2, 3, 4, 5, 6, 7. In this case, 7 frames. You know what I'm saying? So we have focused on at the center here one frame spacing before. So yeah, this is just like sliced model, 1 frame spacing, and it was nearly 4 to 5 meter the length. And here they are talking about the material properties. So I want to give you some time to think about why they apply the high tensile steel for the deck and the outer bottom as well as inner bottom. But at the same time, you can see here this is side shell, the outer side shell as well as inner side shell. The material properties you can see here, they just simply apply the mild steel. We should remind that the yield strength for the mild steel, it was nearly 235 megapascal. At the same time, the high tensile, this is exactly the same as H. Looks different expression, but exactly the same meaning. This is yield stress 313.6, or in general we just simplify like 315 megapascal. So those two values are not same, which means that this is much better than this mild steel. But why we apply this better or higher yield strength material? The reason is once ship is subjected to the vertical bending moment, sagging or hogging, at the center the stress will be, stress distribution at the midship section. It will be like this. For example, the sagging bending moment is applied, the deck part will be compressed. At the same time, this outer bottom part will be tensioned, isn't it? So anyhow, this is neutral axis, for example, and deck and outer bottom, and higher value of the stresses will be applied to the deck as well as outer bottom. That's why they have selected different material at here, outer bottom, deck, but here just normal materials. So deck stiffened panel, now you are familiar with this plate and stiffener combination model, and this is unstiffened plate or just plate as well. So in general, we defined the length of the plate is A and B is plate width. Of course, the thickness can be defined as the T. All right. And side stiffened panel, nothing special, just rotated 90 degree. But here we have the, stringer, like here, the first one, second one, third stringer, and you can see the bottom structures here. You can understand what I'm talking about, and bottom stiffened panel as well. So At the same time, we can see the offshore platforms as well. This is the column structures, and this is also the combination of the plating and the stiffness. So here, I've introduced this before. Once the vertical bending moment is applied to the structures, what will happen? So we will try to apply the pure bending moment to the one frame section, as you see here, and this angle will be changed, which means that the curvature will be changed, and the shape will be like that, which means that the bottom structure will be tensioned. At the same time, the deck will be compressed, and load effect due to the global response and strain and stress will be changed. And at the same time, we can focus on the here we just apply the banding, and we will see the one single fiber here at deck or the bottom due to the bending load. And if you see this one single fiber, it will be compressed. We started from the bending moment, but now we are talking about actual compression or actual tension at the bottom. And this is one of the simulation result by commercial software. And as you can see here, this is for your information. This S represent stress, and this number one in general represent X direction. So this is common sense in the case of ship structures. So length direction is X, and width or the breadth direction is Y, and the height or the depth direction is Z. So this one, or in general, we put 1, 2, and 3. So now you can understand stress S1 represent exactly same as stress X. Okay, so I think they did not apply any load like bending moment. That's why you can see the color here. This is exactly blue. You see here the stress level is 0 at this moment. But once they increase the vertical sagging bending moment, you see here sagging bending moment is applied, then the deck part will be compressed. At the same time, the bottom part, the bottom is tensioned. That's why tension in general we use positive certain value, and negative represent compression. That's right. You can see the shape here. Later I will introduce buckling behavior, but here the shape is not like that. Just only the color has been changed, and then they will increase the bending moment value. Then here you see the stress values are increased from here to there, right? So this is stress value, but exactly same time they have checked the one more time. They increased the load one more time, and you could see here the totally collapsed, like here the buckled part at the deck. And at the same time, they have checked the von Mises stress. You see here. So this is common sense. You need to. I'd like to suggest you to check what is the von Mises stress. The definition is this von Mises stress is used to predict yielding of the material, yielding of the structures under complex loading applied. Because if you want to understand this, if let's say we have applied the stress X, for example, stress X, like here, last time we have learned about Mohr circle method, stress X, stress Y, and tau XY. Then how are we gonna combine it together? This is a little bit similar question on this, and one single value can be suggested about, okay, the stress level will be like that. So what we need is for mice as stress criteria. This is one of the criteria. Of course, we have furthermore stress criterions, but as you can see here in here, if we discuss about the stress x and y direction only, then it could be simplified from this equation, like this represents stress x, stress 2 represents stress y, and here stress 1 is stress xy. This is exactly same as stress. You know what I'm saying? Because x, y, z, it was number 1, 2, 3. So substitute it exactly same as that. So this is pure axial loading in x direction, y direction. So in here we don't experience any shear loading. Sorry, about the jet direction loading. So neglect tree, and tree here, so that you can simplify it like that. All right. So based on this, they have plotted the stress contour again based on this. So red color, in general, as a structural engineer, we should be able to avoid this very red colored region here. As you can see here, the maximum stress 313.6, that was exactly same as the yield stress of the high tensile steel. So this means that this red colored region, it is already reached yielding part of the material, so it will start to the plastic deformation will be started. So actually we don't want it. So here you could see the simulation result, and however the strength is directly related to the strength of deck in this case, once because we apply the vertical sagging moment so that the deck part is compressed. We can see the buckling behavior. In the case of hogging, we need to check this, the bottom, inner bottom, or the outer bottom part, as you can see here. And let us simplify it, like plate stiffener assembles. And as I explained earlier, plate stiffener combination model is here. And the question is, can it represent the entire panel? Of course, yes. Like simplest approximation technique can be applied. So like that, PSC model. And there are several types of the stiffness, like flat, bulb, angle, and tiba. In general, we love to use the flat, T, and angle. So we learned about how to calculate the moment of inertia values. Like sectional area is not difficult for us. The thickness times the height, and this is come from here as well, like BT square over 12. You might be familiar with this. And for these, we have learned about the concept of the moment of inertia. So the first we need to calculate, define the neutral axis position, and then based on neutral axis we can calculate INA, the moment of inertia value at neutral axis. You can understand what I'm talking about. In the case of angle, same procedure, and plate stiffener combination, simply we code again PSC model. So it's nearly same. Neutral axis position will be changed based on the given geometry and the shape and thickness, and other types exactly same. We can do the calculation. And now this is related to the tubular members, like topic if I'm not mistaken, 13 to 15 will be the truss members. And you can see this is fixed offshore platform to produce the oil and gas from the offshore. So those tubular members, we will focus on that. And this is also considered as the beam column. So it can be simplified like that. And this can be considered as the free body diagram we learned many times. And simply supported condition, we can see the joint to connect all those 1D structural members. So pin jointed frames, truss members, we will have a look on that. And actual load will be applied, treated in topic 13 to 15. No worries, I will introduce one by one later. And one simple question is, this looks like fixed jacket platforms, and of course the water level will be like, the water level will be like that. And on top of these jacket structures, we're gonna have this kind of the top side platforms to produce the oil and gas. Actually, it is connected to the riser, and of course this is seabed. We need to drill it and find the oil and gas. And here we will the first step for the production will be done here, and then basic function of this offshore platform, like here, is separation. Like that's just like we call the cocktail, like the oil, gas, mud, water, everything is mixed. So we don't want to transport these kind of cocktails. So once we do the separation work at here at the deck top side, we can just simplify it like, oh, okay, we don't need the water, we don't need mud, but what we need is the oil and gas only. So produced separated oil and gas will be transferred to the onshore like that. Sometimes the vessel, the crude oil, the oil tanker will come and transport it, but most of the time the subsea pipeline might be the economical options. So here, this is tubular members, and the section they are introducing the thick and the thin walled. They define that the R over T thickness is less than 20, or over 20. They define this is thin wall and this is thick wall. And based on that given information, we could simply calculate the moment of inertia values. So it might not be difficult for us to calculate this in the case of these thin conditions, which means that we'd like to neglect the effect of the thickness. So as you can see here, the tip, you can be able to drive how they get these I values. So load and load effect, and this is simplify the beam structures, lateral load Q applied, and boundary condition given. So we have derived the simple beam theory and bending stiffness here, and this can be, you can remember the simple beam theory, the bending stress, that was moment Y over I, and we can simplify this part again, over jet is I over Y. We called section modulus, sometimes they called S or jet. So beams carry lateral load, and the load effect will be the bending moment and shear force. So here we can discuss about the actual loading conditions. In this case, this is the normal stress, that is apply the actual force over sectional area, and this is we've learned it like Hooke's law. So E epsilon, or you can plot it like stress epsilon, and here, so this is like E epsilon. So this is elastic region, so that we can drive all those details. And we have learned that the definition of column is one-dimensional element, structural element subjected to the compression. We can see the column in all buildings, and the road is like the 1D structures but subjected to the tension. So you can simply see those figure. And combined loading, in this case beam column, 1D structures subjected to the bending as well as the compression. So yielding meta and buckling induced collapse, this is truly important. I have to highlight this part for you to understand. So basically, global structural analysis, local. This is the main difference. Once we apply the vertical bending moment to our structures by global structural analysis, we can do the safety, we can assess the safety of hull girder, which means that bending moment my over I, so that we can get bending stress values, and then these values will be compared with the material properties like yield stress. Of course, these should be better than these, right? So that we can think that, oh, in the global perspective, our structure will be safe. But why we need to consider buckling behavior? I have not explained about the buckling yet, but this is one of the reasons that we need to consider buckling. So we will bring these stresses obtained from the global structural analysis. But the other thing is here, buckling can cause the collapse, which means that the buckling stress can be much smaller, lesser than yield, but it can introduce the collapse. So we need to see this local behavior from now on, right? So how are we gonna, obtain the buckling stress? That will be covered in topic 10 to 12. I will introduce it, all the derivations, including the boundary conditions, basic concept, fundamentals, and existing empirical formulations, design formulas, how we're gonna apply it, all those things, I will introduce it. So basic procedure is first do the global analysis and get the bending stress and compare it with the material yield, and then bring this information to the local that will be applied to our local structure. For example, this is plate or the column that will be subjected to certain value of the stresses obtained from the global, and then we will check this local structural safety, that is number 2. So global okay and local okay, then we could say that our structure will be safer, right? So like this, in the case of global, we will see the trend will be like that. The stiffness and ultimate strength will be compared with the yield. But in the case of local, we need to see this kind of the buckling, right? So this is actual elongation case, but if the structure is compressed, like we call the actual shortening curve, and critical buckling strength must be confirmed from local structural analysis. That's why I'm introducing those two values. The criteria is yield stress for the global, but the local strengths, we need to check critical buckling strengths to avoid the collapse. So in stability problems, this is one of the issue for the buckling, but I'd like to define the buckling like first cylinder structures, compression applied, and once we apply the actual compression like this, the structure will be buckled like this way or that way. Look at the direction of the deformation. This is exactly perpendicular to our applied loading. So it will be perpendicular to applied loading. This is applied loading direction, but deformation will be like that. So this is my definition of buckling. right? So here, boundary condition, almost done. We have learned about free boundary conditions. Actually, our ship structure can be considered as free boundary condition. We don't have any boundary effect at that. And roller, we've learned that, but you should be able to understand the mathematical expressions like vertical reaction force. We hold it, and here is the roller, so we can move those two, but this way movement is not allowed. No moment, because this is simply supported condition like the roller. And lateral deflection is restrained. And simply supported condition, you can see that this is not the roller, which means that we can't move like that. And have a look on these kind of boundary conditions. And previously I have introduced many times about the, for example, simply supported condition, deflection, slope, and moment. Do you remember? Like simply supported and clamped condition, and deflection case at here A and B, that should be, deflection is this way, it should be 0, no deflection. In the case of slope here, because this is simply supported condition, so slope is maximum. But in the case of clamped conditions, they don't allow to have this slope, because once we apply the load, in the case of clamped conditions, it will deform like that, which means that from the beginning at the end, the structure will maintain this straight line. So it is 0 at A and B. In the case of moment, because in the case of simply supported case, moment, it must be 0, which means that moment free at the end. But here, clamped condition, they hold it restrained, so maximum moment will be applied. So this is important. We will utilize this in topic 11 for our derivation part. At the same time, clamped, I have introduced this before, and fixed and clamp condition. The difference is this looks like roller, but this is not allowed to be moving to left to the right. So reminder, in this session we discussed about basic concept for the global, local, how we gonna connect it, basic concept for the structural analysis, safety assessment, and now we could be able to understand ship structural analysis, column, offshore structure, truss members, failure, and buckling, boundary conditions, something like that. But all the details will be introduced again, like here in topic 10 to 11, 12 will be the column, the buckling methods, collapse strengths, and truss, mass of joint, and section method. I will introduce truss members, how we're gonna utilize it for offshore structural design, and last part will be the statistical analysis. So that's all today, and 감사합니다. Thank you.